Moonlight lifts a pale road across the surf. A heavy shape heaves from the water, sand hissing under its weight, flippers pressing a slow stairway toward the dunes. The horizon is empty. The tide breathes. It has crossed gyres and storm tracks, slipping through cold tongues and warm eddies, guided by cues that leave almost no trace. This is marine reptile migration at full circle. The pit forms with each sweep, eggs lowering into a chamber hidden from stars and crabs. The work is precise, unhurried. The hole is sealed. Tracks are brushed away. A pause. Then the ocean takes the traveler back, the reptile that crosses oceans to the same beach. For millions of years, a wide-roaming marine reptile has split its life between open water and brief landfalls. Juveniles ride currents that function like moving pastures. Subadults graze seagrass and algae on shallow banks. Adults range far. Males rarely return to shore. Females haul out to nest at night when heat and predators ease. With slow growth and late maturity, often decades, the rhythm favors patience over speed. Only after this long apprenticeship does the pattern sharpen. Now the name fits, the green sea turtle. Across coasts and islands worldwide, green sea turtle migration threads ocean basins and returns to familiar coves. The evergreen anchor stands, navigation so precise that an animal crosses oceans to the same beach where it began life. Here is the paradox, stated plainly. How do sea turtles navigate with such pinpoint accuracy across entire oceans? Satellite tags trace lines that span thousands of miles, then narrow to a single strand of sand. Females emerge within a short window each season, many returning every 2 to 3 years. The accuracy is startling. Individuals reappear at the same sea turtle nesting beach within tens of meters, despite shifting currents, drifting sargassum, and coastlines that change with storms. Hatchlings leave under moonlight, swim through the surf zone using wave cues, then vanish into pelagic nursery grounds for years. When they grow, they adopt foraging sites separated from nesting beaches by entire gyres. Decades later, they come back. The ocean offers no signposts, no fixed scents beyond the continental shelf, and light fades quickly. Yet homing persists across magnetic storms and secular drift in the Earth's field. Drift experiments, current models, and tag data suggest a mix of straight courses and wide detours, but the endpoint remains the same. The precision often reads as impossible to explain with any single sense, and scientists still debate how map and compass combine across so much moving water. Evidence suggests a layered toolkit. One leading hypothesis is turtle magnetoreception paired with magnetic imprinting. As hatchlings crawl seaward, they may encode the local magnetic signature, inclination and intensity, as a lifelong reference. In adulthood, they detect broad magnetic gradients that operate like isobars on a chart, guiding long legs of travel. Where lines converge, the magnetic address of a region emerges, helping redirect when currents push them off course. The trade-off is resolution. Magnetic maps are coarse. Variations caused by iron-rich rocks or field anomalies could deflect routes. That may explain why arrivals cluster along stretches of coast rather than a single point. A second hypothesis emphasizes olfactory landscapes. As adults near shore, chemical cues from rivers, reefs, or seagrass beds might form an odor mosaic. Individuals could recognize a familiar blend linked to their natal cove. This would refine position when magnetic cues grow noisy near land. Yet offshore scent plumes are intermittent and easily scattered. A third hypothesis, supported by orientation trials, invokes a hierarchy of cues. In the surf, waves provide a compass. Hatchlings and adults align to the dominant direction of wave propagation, then switch to celestial or magnetic information when swells confuse. Layered behaviors reduce error, stroke long with the field, correct with waves and odors, then cite coastline topography in the final approach. None of these alone solves turtle navigation ocean scale. Together, they begin to fit. Field data on green sea turtle migration align with this multimodal view, but the weighting likely changes with weather, experience, and local geology. Midway through the season, a tagged female departs a feeding bank and draws a clean arc on a tracking map. Days pass. The line bends around eddies, holds course across open blue, and tightens near shore. She surfaces at night, takes air, and glides over reef ledges she has not seen for years. The beach rises like a memory given form. Sea turtle nesting beach fidelity looks absolute from shore, yet the ocean path is messy. Some females arrive late, some overshoot, then correct along the coast. A few skip a cycle entirely, their signals gone quiet, their routes untraceable. Whether they died, re-nested elsewhere, or simply shed their tags, nobody knows why. The pattern endures all the same, the reptile that crosses oceans to the same beach, and each return lands like a small data point, rewriting what we thought we knew about long-distance homing. Before sunrise, tracks stitch the sand in parallel lines that the tide will erase. The nester rests in the backwash, takes on weight, and disappears into the dark. The question lingers in the wake. Can memory be written into the body itself? If the map lives partly in a field we cannot see, partly in chemicals drifting from a living coast, and partly in behaviors learned through years of survival, the answer will stay provisional. The ocean keeps its noise, the traveler keeps its counsel, and the circle closes again. One more crossing, one more precise landing, another clue that waits just beyond the dune.